I think so. We'll see. Yep. Am I audible on the? Okay, great.
Okay, our next speaker will be Abhishek Uppar.
Shouldn't touch the wires. Okay, let's do this. Hi everyone, I'm Adithya, and today I'll be talking to you about our work in exploring a new style, perhaps a new paradigm of for providing guarantees for software. This is joint work with folks at the Indian Institute of Science, Bangalore, the University of Illinois Urbana-Champaign, and I'm at the University of Wisconsin-Madison. I want to start by getting us all to think about what the state of automated verification is today. And if you think about it in the landscape of specification complexity and code size or code complexity, we really have an either-or kind of situation, right? So you can have your favorite separation logic, recursion, quantifiers, what have you, and then if you want automated verification, you really can only do smaller programs. Or you can have something like lightweight types, and then you can really scale guarantees to large code. But when you have both complex specifications and large code, there isn't really like a systematic study or a science behind how to kind of approach this problem. And in our paper, we focus on a particular use case where you have a smaller client that uses a larger library. Now, this is actually fairly typical for a large class of programmers because, a lot of programmers, they don't really write libraries on a daily basis. What they do instead is they write smaller programs for their particular applications, and they just use convenient abstractions that are established and available elsewhere for, managing a queue or, calling things over a network and so on. And so this is the problem that we look at in this paper, and we want to think about how do you establish guarantees for this kind of software. So, in a nutshell, this is the one-liner of the entire work. Our argument is that you verify the client and you test the library. Let me say that one more time. You verify the client, but you test the library. Let's actually look a little bit into what this means. In classical verification, when you have this like client calling a library kind of setup, what happens is that you have to come up with contracts at the interface for the library methods such that on the one side, you verify the client assuming the contracts for the library that you came up with. And on the other hand, you also have to show that your library methods do indeed satisfy these contracts. What we're recommending is that you just drop the latter condition and you test the contracts instead, right? Let's, you might be asking, why is this a reasonable thing to do, right? Like, what am I talking about in terms of verification? And to do that, let's zoom out a little bit and think about what we mean by guarantees for software, right? So you're really thinking about the situation where you're writing a smaller program and you want to avoid bad code, right? You want to avoid, doing something stupid in your code. But if you're writing a smaller client that's calling the standard Java container for queues, it is very likely that you're not going to have these bad behaviors inside the library. What's more likely is that you're going to have these bad behaviors inside either your own code or in the way that you're calling the library, right? So if you think of this as the kind of threat model or the kind of bad code practice that you want to avoid, what then falls out is that maybe it's reasonable to make sure that you verify whatever you're writing, the suspicious part, very, very well, modulo a high confidence abstraction of something that is more well established. And so that is, in a nutshell, the essence of the paradigm, right? So I want to formally define what this is. We call it the VMTLC problem, the verification modulo tested library contracts. Given a client with some specifications, which calls a library, you synthesize contracts for the library's methods such that A, you verify the client assuming these contracts, and B, a test generator given a bounded resource budget does not find any input that violates these contracts for the methods. Now, mind you, we are in the setting of completely automated verification. So when I say you have to verify the client, if the client has loops or anything else, you have to come up with loop invariants or any other annotations that are required. So that is the problem. Okay, let's just look at an example to shore up our intuition, right? So here is an example of a client that uses a set library. In this work, we operate in the setting of object-oriented programming. So we have encapsulation, so you don't get to peek inside the implementation of the set. What you're given instead is a set of observer methods. This is a fairly standard thing to do in object-oriented verification. Observer methods are like mathematical functions, essentially. They're side effect-free code that give you a view or a measurement of an object at a particular point. And so for a set, you can have observer methods like, is the set empty? What is the size of the set? And what is the minimum element in the set? Right? So these are some observer methods that you can have. Now I also have a client for you. This is a simple one for the purposes of this presentation. It has two loops. In the first loop, it just adds a bunch of non-negative integers. In the second loop, it drains the entire set and adds them all to an accumulator called sum. And what you have to prove is that the sum is non-negative, which of course it is. So given the VMTLC problem we've just looked at, I want to come up with contracts for the methods that the client uses, namely insert, remove, and empty, such that, as well as loop invariants for the client for the two loops, such that I can verify the client, and then separately, I can also test the contracts that I came up with for these methods and make sure that I can't find any input that violates these things. In this work, we encode verification conditions as constraint horn clauses. If you are not familiar with CSCs, ignore this slide. For the people who are aware, we encode them as CHCs. And so basically, you have unknown predicates corresponding to the two invariants, as well as the contracts that you want to come up with. And the verification conditions say exactly what you want, right? The beginning to the loop invariant, and all that stuff. Okay. So here are some contracts that you can come up with. So for insert, you can have a contract like if you either have an empty set or you have a set whose minimum was already non-negative, and you added another element that was non-negative, then you get another set whose minimum continues to be non-negative. And you can do similarly for remove, right? If you have a set whose minimum is already non-negative, anything you pull out of it is also non-negative, and then you have a set that continues to be minimum non-negative. Okay, and the loop invariants say exactly what you think they say. The first loop that adds the elements into the set says either had an empty set, which is the beginning, or I have a set with a non-empty minimum, with a non-negative minimum. And the second loop says either I have a set with a non-negative minimum, or at the end the set will be empty. And crucially, these invariants are maintained by the fact that the contract for insert and remove promise you that after you insert or remove, you continue to get sets with non-negative minimum. And using that, you can prove that the accumulator remains non-negative at the end. Good. Now, this is standard verification. We are familiar with this. But then you also want to make sure to have a test generator throw a bunch of well-behaved, well-formed inputs at these contracts and make sure that you can't find any behaviors of insert, remove, or empty that violate the contracts that you've come up with. So in contrast, if you had come up with something like, you know what, insert is going to be such that anything I insert, I'm going to get a set whose minimum is non-negative. The test generator, it'll clearly help you prove your client correct, but a test generator can easily say, you take the empty set, you insert like -5, and then clearly your contract is not true. So that's how that works. Okay, so we've gone through this exercise of verify the client, test the library. Now that's the first contribution of our work. Before I talk about the second contribution, I want to take a moment to reflect on what the real problem we're solving is, right? Once you think about this kind of hybrid guarantee that's not really testing, that's not really verification, it's kind of somewhere in the middle, and then you think about what you're really wanting the guarantees for. You want guarantees for the client program that you're verifying, right? We've established this at the beginning numerous times. So if what you want to do is prove your client correct, then the abstraction that you need for your library really only needs to be the abstraction that you need for your client, right? You only need a view of the library insofar as it is useful to prove your client correct. Now, what this opens you up is this idea of a contextual contract, right? So you have modular contracts, which we're all familiar with, and I presented to you. These are contracts for library methods that are universal. They hold for all possible inputs. In another sense, they basically are true for any client that might use the library methods. On the other hand, you can have contextual contracts, which you have one contract per call site. So if my client had 2 calls for insert, I'll have 2 contracts, one at each call site, such that these contracts are valid at that particular point in the program. And what this amounts to is really you're saying that they're valid under an implicit precondition. And what is the implicit precondition? You just collect all the reachable states that get to that point of the program and say, under that precondition, this contract is valid. That's what a contextual contract is. Now, why are these useful? Well, because they can actually give you a lot of leverage and can be much simpler than modular contracts at times if you want to establish guarantees about your software. So here's the example again. This time, I'm not going to give you the observer function min. And this is a problem because I liberally used min in my example earlier. I told you things like if you had a set with a non-negative minimum and you did something, it'll continue to, like you can't do any of that right now. And first of all, you have encapsulation. So you cannot break encapsulation, look into the set and go, you know what, I'll just write a minimum function. Like that's not happening. Secondly, even if you somehow manage to do that, you probably have, let's say, it's implemented as a list, and then you have to write a recursive function to compute the minimum, and then your verification goes for a toss. It just becomes much harder. So modular contracts, you're going to have to do a little bit of gymnastics, and then maybe it might or might not work. In contrast, look how absurdly simple a contextual contract is. You just say, let's say for remove, no matter what element I pull out, it's going to be non-negative. And why is this okay? Because under the implicit precondition at that call site, it is in fact true that no matter what element you pull out of the set, it's going to be non-negative. I really only added non-negative elements to the set, so of course it's going to be true. So contextual contracts in general can be simpler and easier to come up with. And they still help you construct a kind of this hybrid guarantee about your client code. The third contribution of our work is to come up with a solver, a pipeline for establishing these VMTLC style guarantees. And this solver has an interaction between a generalizing CHC solver, I'll tell you what that means in a second, and a test generator. The CHC solver is given the verification conditions for your client, and the test generator is given the code for your library methods. What happens is that the solver tries to come up simultaneously with loop invariants and contracts for your library methods. Once it does that, it sends the contracts over to the test generator. The test generator then looks at the contracts. If it's happy with them, yay, you're golden. If it's not happy with them, it'll come back to the solver and say, no, these contracts are not right. Here's an example. And the solver takes those failing examples into account and tries to come up with another set of appropriate loop invariants and contracts that can still verify the client. And this loop keeps happening until both entities are satisfied. Now, one of the key things that we realized while doing this work is that you really need a generalizing solver and not just some CHC solver. And why is this? It's because if you encode the problem at hand as a CHC along with all these like extra things saying, oh, all these buggy things that I've found for buggy instances I found for previously proposed contracts should be avoided, a generic CHC solver can just keep narrowly avoiding this and keep giving you like contracts that are still slightly wrong. Whereas you really need a solver that looks at all these failing examples that you give it and say, you know what, all these are symptoms of something else that has to be satisfied, namely the test generator, which is like hanging out in the back and it has some hidden expectation, and tries to come up with a general contract that will satisfy both requirements. And I'll show you some experiments where we tried like a regular CHC solver. In our work, we implement a generalizing CHC solver using the combination of an ICE learner. This is a learner established in prior work. I'm not going to go into it during this talk, as well as a regular constraint solver. And what ends up happening is this like very nice inner learning loop that happens inside this outer learning loop that between the solver and the test generator itself. There are more details in the paper. I would really encourage you to look at it. Okay, with that, I really want to move on to talking about the results of the paper. I'm going to flash some numbers and talk about what our evaluation revealed to us. We implement 3 learners for our ICE learning for the contract and loop invariant synthesis. We used Horn ICE, which is an ICE learner from prior work. It synthesizes decision trees. We also just threw an LLM at the problem, because, well, of course. And then we also constructed a hybrid solver that comes up with flexible, can flexibly come up with atomic predicates, which are then fed to the decision tree learner. And so these are the things that we came up with. Crucially, even though we use an LLM, mind you, all the contracts are vetted, like doubly vetted, on the one side by testing, on the other side by verification. So you really cannot get away with proposing unsound things. We implement these in a tool called Dualis, and we evaluate Dualis on a suite of benchmarks drawn from real-world libraries and competition problems. Crucially, we wanted to make sure that our problems are beyond the state of the art, so we threw all of these problems at Seahorn, which, as far as I know, is one of the state-of-the-art tools for completely automated verification. And Seahorn could only solve 7 out of the 43 problems in our suite. And more importantly, it was bad even when we gave it the library contracts. Right? And this really shows that the size of the problems and the complexity of specifications really do lie beyond the state-of-the-art. And we have libraries that are like up to 3,000 lines of code. Here are some evaluation results. It should be surprising to absolutely nobody that LLMs are doing very well. But I would encourage all of you to take it with a pinch of salt, because I think there's a lot of headroom for the hybrid solver to do better. We're looking to doing a larger study, and I think some of these results might change. What I do want you to pay attention to is the fact that when you ask for guarantees to be established using contextual contracts rather than modular contracts, you get better numbers, right? Because contextual contracts, as we discussed in the example, can be simpler and easier to synthesize in many situations. And the experiments reflect that. Okay, so the second I said testing, I know like 90% of you have been waiting to ask, are the contracts valid? Don't worry. You are my people, I've got you. We did absolutely do this study. We looked at all the synthesized contracts, both modular and contextual, for all of the benchmarks in our suite, and all of them were correct. We believe we did a mix of manual and automatic vetting, and with high confidence, we believe that all of these contracts are indeed correct. Now, we also did this experiment on an adversarial suite where we constructed programs where we artificially injected bugs that are hard to find for a test generator. By that I mean like we injected these very long paths that are rare and it might be hard to get to these points. We injected such bugs. And even in that suite, for about 30 programs, when we asked our solver to come up with modular contracts, it said, no, I cannot come up with any, which is good. They're wrong. You should not be able to come up with contracts. And this speaks to a subtlety that, in the work, which is that it's actually pretty hard to come up with a generalizing hypothesis that somehow satisfies a test generator, helps you prove the client, and is somehow still wrong, right? And I think there's something in there that is worth exploring further. Now, of course, this was not true for contextual contracts. And for our 30 programs, there are about 11 programs where the solver came back and said, hey, I found a contextual contract, and it should not have been able to. We also looked at just using a plain CHC solver. I think we used CVC5 instead of a generalizing CHC solver, and it performed pretty badly. So it really looks like this idea of generalizing from the failures and having it be incorporated into the contract and loop invariant synthesis is essential. Okay, with that, I'm done. So my takeaway, this is the mantra, right? Verify the client, test the library. That's what we're advocating for. And in doing so, we've, I hope I've presented to you the possibility of a new point in the design space for establishing guarantees for software, this paradigm of VMTLC, verification modulo tested library contracts. I've also introduced to you the idea of contextual contracts that can be stated in the client's calling context, which may be simpler to state and synthesize, as well as a counterexample guided learning framework that combines a test generator and a generalizing solver to establish VMTLC style guarantees. Thank you. Oh God.
Hi, Michael Emmy from Amazon Web Services. Really interesting talk. I'm just wondering what you think about the potential risk of contextual contracts relying on implementation details that are not like totally stable and are kind of not the encapsulated object, but kind of maybe like a hash set would satisfy this, but a linked hash set wouldn't.
I see. Okay, let me try and repeat your question to understand. What do I think about the possibility that contextual contracts might end up relying on implementation details as opposed to the interface itself, where you have like one kind of hash set versus another kind of hash set? Is that the question? So I don't quite see why that would be. Like, do you have some intuition for why do you think that might be the case? I don't see that as being a risk, right? I mean, in contrast to modular contracts, somehow you seem to be contrasting with modular versus contextual, and yeah, I don't see why.
You have a set interface in the current implementation that you're using is like a tree set which returns first like the minimum element or whatever it is, and then later, someone wants to change that to a hash set or some other kind of, then you would really be relying on the underlying, sortedness of that data structure that's not part of the set interface.
Right, but this is also true for modular contracts, right? In the sense that what if you observe behaviors and your vocabulary allows you to express something that is very specific to the implementation? Is that right?
Yeah, but the modular set contract wouldn't, appeal to a specific order there in that case.
Right. Yeah, it's an interesting question. I think maybe it's worth talking more offline, because I think there is some, okay. So first of all, there is an element of generalization involved, and clearly modular contracts generalize more, which is why you would avoid things like these implementation details. One of the things that is the hidden element that I have not spoken about at all in this talk is the vocabulary, right? So if you have a good set of observer methods, I would suspect that it might be possible to avoid over-relying on implementation details. Now, there is other work that we've cited enormously in the paper that tries to synthesize like very strong contracts and things like that. So you might want to consider synthesizing even contextually a stronger contract, and maybe that'll avoid the kind of problem that you're talking about. So I think of this as a generalization issue, the way, does that make sense? And I'm happy to talk more offline.
Miriam Kim at UCLA. I have a question about test generator part.
Yep.
Like, so it seems like you are checking contract like by testing the libraries, but AFL++ is not a property-based testing; it's just a fuzzer. So I'm kind of curious about how you actually test the contract. Because AFL will require like driver generation or fuzzing entry point, right? And the second question related to that is that for like contract that involves like stateful effect, how do you model the driver generation?
Okay, I understood your first question, so I will answer that, and then we will get to question number 2. The first question you're asking is, what is the entry point for the tester, and how do you construct the test harness, right? So the test harness is, roughly speaking, you just construct a bunch of well-formed objects, a random set, and you test with those set of randomly selected well-formed objects. In an earlier version of the tool, we used PECs, but for numerous reasons, we moved away from it. So there's no fundamental reason you can't use a property-specific test generator. In fact, in my opinion, it's better to use something that's property-specific because we're trying to look for contracts that prove a specific client, right? So, and for contextual contracts, you construct well-formed objects and all that, but you make sure that the entry point is only through the client. Right, so you construct well-formed objects not for the library methods, but for the client, and then you then like take the reachable path, and those are the inputs that you take. So I didn't quite understand question number 2.
The question is related because basically it's also about like constructing the program state where the client library could be invoked, right? So I think you mentioned that you're doing it through the client like program invocation, but we could talk offline.
Yeah. You just have to figure out what the randomly constructed constructing well-formed objects is fine, right? That's obvious. And you then have to figure out what the entry point is. For modular contracts, the entry point is the library method itself, which is just tested in isolation. There's no context to the client. For the contextual contracts, you reach them through the client. So you write a test harness that is specifically constructs calling the client first, and then via that you go to the particular libraries. And yes, for what it's worth, I do think we should be using property-specific, property-driven test generators.
Okay, I'd like to keep us on track so you all can get to lunch on time, so let's move on to our last talk.
Yep, thank you.